Hi class, welcome to lesson 53, the second lesson in Unit 9, Kinetics and Equilibrium. In this lesson, we are going to explore potential energy diagrams. By the end of this lesson, you should be able to determine if a reaction is endothermic or exothermic based on a potential energy diagram, label all the parts of a potential energy diagram, calculate heat, and draw a catalyst in a potential energy diagram. Let's get started. Potential energy diagram shows the changes in potential energy or stored energy when a chemical reaction occurs. All chemical reactions occur when reactant particles collide with sufficient energy and proper orientation to make products. The thing we should do is look at what a potential energy diagram looks like. So, on a potential energy diagram, the potential energy, also known as heat, is the y-axis, while the time, reaction progress, or reaction coordinate, all meaning the same thing, is the x-coordinate. And when we start with a little line here on the left. We start on the left, and this will represent the potential or stored energy in the reactants. This value always begins on the left for a forward reaction because the reactants are on the left of any chemical reaction. In this example, our reactants will be 2 moles of hydrogen gas and 1 mole of oxygen gas. So we'll have to put in some energy to allow them to collide with sufficient energy and proper orientation to break bonds and make new ones. This total amount of energy when we talk about. So when the particles that are reacting are in their perfect orientation with sufficient energy, they have formed something called the activated complex. We can use the energy of the activated complex and the energy of the reactants to determine what is known as the activation energy, or the minimum amount of energy needed to get the reaction started. Our potential energy diagram is finished by drawing another horizontal line representing the potential energy of the products. So for this particular reaction, the reactant hydrogen and oxygen molecules have formed the product's water. Now, what we can do is, based on the potential energy of the products and the activated complex, we can also determine the activation energy of the reverse reaction. So the reverse reaction would take the water molecules and break them apart into their hydrogen and oxygen original. The last very important part that we want to label on our potential energy diagram is the difference between the potential energy of the products and the potential energy of the reactants. This is the delta H, or the heat of the reaction. In every potential energy diagram, you're going to have an input and a loss of energy. So all of them should have 2 horizontal lines with a hill in the middle. Remember, this ties into what we discussed in the beginning of the year. Breaking bonds requires energy, and making bonds always releases energy, but potential energy diagrams tracks the changes in the total energy for the entire reaction, which involves many bonds broken and many bonds being formed. Now what we're going to do is compare the 2 types of potential energy diagrams, endothermic and exothermic diagrams. We know that an exothermic diagram occurs when the products have less energy than the reactants. Why? This is because energy is released as a product. This means that our delta H will be negative, just as indicated on reference table I. Recall that delta H is the products minus the reactants. So here our delta H will be. Endothermic is the opposite. On endothermic reactions, the products have more energy than the reactants because the energy has absorbed heat as a reactant to produce products with a higher potential energy. In this case, our delta H will be positive because delta H again is the products minus the reactants. Let's take a minute to summarize your learning thus far. By now, you should be able to determine if a reaction is endothermic or exothermic based on the potential energy diagram. Now we're going to review the parts of a potential energy diagram. I've given you blank potential energy diagrams in your notes that you can label. make sure you're using your guided notes. We've already reviewed the general parts of potential energy diagrams. Now we'll see how their positions on endothermic and exothermic reactions differ. The first position we'll look at is the activation energy, which is the minimum amount of energy required for the reaction to occur. The activation energy is always going to be the difference between the reactants and the peak of your curve. So let's look at our endothermic curve. We can see that our reactants begin with a potential energy of 50 kilojoules. So the activation energy is the amount of energy needed to get the reactants to the top of the bump. So our activation energy would be 150 kilojoules, so we could get to the peak of our reactant. An activation energy could be a spark or heat or any force that's going to start the chemical reaction. If your reaction does not have sufficient activation energy, then no reaction will occur. For the exothermic reaction, the activation energy is still the difference between the reactants and the bump. But in this case, our activation energy is only 50 kilojoules. So we need a lot less energy to get this reaction started. But if we don't have 50 kilojoules, then no reaction will occur. Thermic reactions have significantly lower activation energies. They tend to be spontaneous or favored by nature. The activation energy always correlates with the formation of the activated complex. The activated complex is always the highest point on the graph. This is the position where the reactant particles have sufficient energy and the proper orientation in order to make a successful chemical reaction. So the energy of the activated complex always goes from 0 to the peak of your graph. On both graphs, my activated complex has a total value of 200 kilojoules. Now let's label the amount of potential energy of the reactants and the products. Just like a chemical formula, the reactants are always on the left and the products are always on the right. So in our endothermic reaction, the reactants have a potential energy of 50, while the products have a potential energy of 150. So in this endothermic reaction, notice that the products have more energy than the reactants because heat was added to the reactants in order to form our products. Now let's consider the exothermic graph. Again, the reactants are on the left, so our reactants have a total energy of 150 kilojoules, but the products have a total energy of 50 kilojoules. So this is an exothermic process because we are losing energy. So now you should be able to identify all the parts of a potential energy diagram. Now let's talk about calculating the heat of the reaction, or the delta H. The heat of the reaction is the products minus the reactants. These values for delta H are listed for some chemical reactions on reference table I. You can also use the potential energy diagram to determine the delta H. So in this endothermic reaction, when we take the products, 150 minus the reactants, we're going to have a delta H value of 100 kilojoules. So in this case, since our delta H is a positive 100 kilojoules, that means we have added 100 kilojoules for this reaction, making it endothermic. Now, when we look at the exothermic reaction, we again are going to take the products minus the reactants. The products have 50 kilojoules and the reactants have 150. So the difference is still 100, but when we take the products minus the reactants, we actually get negative 100 kilojoules. That means this reaction is exothermic and 100 kilojoules of energy is released. Now when we look at delta H, we can see that the synthesis of water is an exothermic process releasing negative 571.6 kilojoules. Now, if we go and we reverse the chemical reaction by beginning with the products and decomposing to the reactants, we can reverse the delta H. So the reverse reaction has a positive 571 kilojoule value for its delta H. At this point, you should be able to calculate the delta H of a reaction. The last thing we want to look at is what happens when we add a catalyst to a chemical reaction. Catalysts are compounds that are neither reactants or products, but instead they are kind of these helper substances that lower the activation energy needed to start the reaction. They do not change the reactants or the products. They just provide an alternate pathway for the reactants and products to collide in a successful collision. So you can see here in red, a catalyst would look something like this. Notice that the reactants don't change and the products don't change, but the middle part of the reaction showing the activation energy is lower. And we'll see the same trend for an exothermic reaction. Again, the reactants will not change and the products will not change, but the graph in between showing the activation energy will be lower. This means the reaction will happen faster. So now you should have met the last objective and be able to draw a catalyst on a potential energy diagram. This concludes lesson number 53. Make sure you've taken good notes, written down the questions you'll bring to class, and completed your homework on Google Classroom. Hope to see you soon. I guess I didn't meet the energy of activation.